Hello, everyone. I'm going to give a quick video about capacitors and RC circuits. So this is some of the stuff that I would have done on the board for lectures 17 and 18. It's kind of spread out over both of those lectures. You'll be glad to note that I paid $4.99 to erase the watermark in the bottom corner so you can see the whole screen. All right. So in lecture 17, you figured out some properties of the most basic type of capacitor called a parallel plate capacitor. And it looks something like this. Give it a little 3D perspective. You've got two big old conducting plates, and some charge plus Q is piled up on one plate, and some opposite negative charge is on the bottom plate. And in lecture 17, you figured out what do the equipotentials look like, what do the field lines look like, and what's the relationship between all of that stuff for this system. That's one example of a capacitor, but there are other types. So in general, a capacitor is anything that stores charge, that it lets a certain amount of plus Q and minus Q build up. And when it does that, there is an associated potential difference, voltage, delta V, between the two ends of the capacitor. So just like a battery or just like a resistor with current flowing through it, a capacitor is something that might end up in a circuit and it might have some delta V across it. And that delta V depends on how much charge is stored, and it depends through the following equation. Q is C times delta V. And I'm going to throw some absolute value signs on here because C is always positive. Q is the amount, the magnitude of charge. So it's how much positive charge is there. And delta V is how big the potential difference is. Now, if you reverse the direction of the voltage, you're going to reverse the direction of the charge, and that you're going to put positive Q on the other plate. C is called the capacitance, and it's the capacity to store charge. So it's how much charge per unit volt, per unit potential difference do you get in the plate. So a big capacitor, a large capacitance, means you store a lot of charge for a relatively small amount of voltage. And the units of capacitance from this equation, we can see they have to be coulombs, where that C means coulombs, not capacitance, per volt. And a coulomb per volt is also called a farad, capital F. And just like a coulomb is a huge amount of charge, and a volt is sort of a normal amount of voltage, a farad is a huge amount, because it's huge over normal. It's a huge amount of capacitance. So you're more likely to see nanofarads, picofarads, or microfarads on your capacitors. There do exist there exist things called supercapacitors that have capacities of up to 1 or 2 farads. Those are huge. They're very dangerous, actually. Okay, so what do these things do? One thing that we can do is we can put them into a circuit. And when you have a circuit that has both a resistor and a capacitor, you're going to end up with an RC circuit. And the symbol for a capacitor in a circuit is derived from what a parallel plate capacitor looks like. So it looks kind of like a battery, but the lines have equal length, and there's only 2 lines. That's important. So what's going to happen if we put one of these in a circuit? So let's say we have just a capacitor and a resistor, and the capacitor has some charge on it, plus Q minus Q. Well, then there's also a voltage across the capacitor, that means there's a voltage across the resistor as well, and a current's going to flow. And a current's going to flow in this direction. The charge wants to get from positive to negative. So it wants to get from high potential to low potential. We'll call that current I. And what's going to happen is that that current is not going to be constant. It's not going to satisfy Ohm's law. Well, the current will satisfy Ohm's law at any given time, but the potential, the voltage across that resistor is going to change as the amount of charge changes. And the amount of charge is going to change as the current flows. And so what we have is a non-equilibrium circuit. It's something that's going to change over time. And what's it going to look like? Well, what happens is the current starts out big because the charge starts out at its maximum. And then over time, the charge gets depleted. It moves around the circuit from the positive plate to the lower plate. That means the Q decreases over time. That means delta V decreases over time because Q equals dV. And that means the current is going to decrease over time. What we have is something that's got to look kind of like this. And in fact, that's exactly what we get. The exact answer, which you have to use calculus to get, is that the current as a function of time is whatever the initial current is, I naught, times an exponential decay, e to the minus t over tau. Now we've seen this exponential decay before. We saw it for damped oscillators, where we had the amplitude was the original amplitude times e to the minus t over tau. And their tau was just something we didn't know what it was. It was how long the spring took to decrease its amplitude by about 1 over e, about 1/3. That's still the case here, but now there's a formula. The formula is that tau equals R times C. So that's nice and easy to remember for an RC circuit. The time constant is RC. And you can check that surprisingly, if I take ohms times farads, I get seconds, which is not at all obvious, but it's something that you should check. The rest of this stuff with RC circuits is going to follow from this relationship. There's one other type of RC circuit that we have to think about, which is an RC charging circuit. This is a discharging circuit. The capacitor starts out charged and becomes less charged over time. A charging circuit might look like this. We start out with a battery and we connect through a resistor to an initially uncharged capacitor. So we still have an R and a C, but now we also have a voltage. Sometimes battery voltages are called EMFs, but you can just as easily call it a voltage. It means the same thing. And in this case, the current does the same thing. The current will decay exponentially. But the charge and the voltage across the capacitor are going to start out at 0 and increase. They increase towards a fixed final value. So these are all things that you can work out the details in the lecture exercises. There's a couple questions on the problem set about it, but that's the big idea. So I hope that's helpful.